All right, here we go. So yesterday we looked at a short video regarding a ice skater. So as that skater was going into that turn, so here we go. We're skating along. We'll put a tutu on, and so skating along, and then what did she do? So she goes into this spinning business. She sticks her leg out. So she's got one leg that's let's have a knee down there and a foot, and then she's got like one out here, and it was doing this business. And these arms were like woo, way out there. And then we go into this spin. Okay. So this was a linear velocity business. Then we take that linear velocity and we start spinning around. And then what did she do?
She brought in her appendages.
She brought in her arms and brought in her arms and her legs and all that kind of stuff. And she was doing this business. So my goodness, we're gonna spin with our arms tucked in around us. Woo, spinning, lots of whooshing, spinning around and around and around and around, very fast spinning. Right, lots of omegas. Even bigger omega. Okay, so how in the world are we going to go from a little initial velocity to a much bigger final angular speed? We can change our moment of inertia, but isn't this rotational kinetic energy in that 1/2 I omega squared minus 1/2 I omega initial squared? And so, here's all right. So, in order though to have this change in kinetic energy, if you think back, we have to have work, and work is force times distance. So, where did this change in kinetic energy? Where did this work come from? If no one's pushing her, how did she do it herself? Yeah, so she does work. So there's work done by the skater and the force of her arms through the distance that she moves her arms and legs in. So she moves her arms and legs in, she does some work, and that's where that change in kinetic energy comes from. Now, in terms of momentum, all right, so linear momentum was what? How did we find linear momentum? Do you remember? Yep. The linear momentum was equal to m times v. And it's a vector. And we should put little vector symbols over it. It does have a magnitude and direction. Momentum can be left, right, up, or down. It can be at angles and things like that. So then our rotational analogy, or angular momentum. So if m is like an I and v is like an omega, and omega even has a direction too. We use the right-hand rule, and if you curl your fingers in the direction of the spinning, then your thumb is the direction of the angular speed. So as she goes into the spin and she's going this way and she curves this way, her angular momentum would be directed up from her feet through the top of her head. So there is a direction, and we use the right-hand rule for that one. Now the symbol for angular momentum is, a lot of times you'll see it as an L. It started out as an angle symbol. from math, the whole like angle symbol. So I tend to draw it like an L that's kind of falling down. That's also kind of trying to look like an old school angle symbol. Okay, so this guy right here is our angular momentum. And it actually has a direction too, just like regular old pimento cheese does. What? Pimento cheese. All right, so I stands for the moment of inertia. And this is our angular speed. So angular momentum would be the unit for moment of inertia. What's the unit for moment of inertia? Do you remember? Kilogram meter squared. And what about the unit for angular speed? Radians per second. And remember, radian isn't even really a unit. It's just make us feel better type thing. So angular momentum would be what? We usually kind of drop the radians at this point because it's not really a unit anyway. Okay. Now, let's see. What? There was another relationship we had with linear momentum. So an object has momentum, it has mass times velocity. And can you change that momentum? Can momentum increase or decrease? Sure, there's an impulse provided. So impulse is the change in momentum. And if you remember impulse, wasn't it that like fancy J looking thing? Impulse was delta P, and it was force delta T, or the integral of f dt. Okay, so could we have an impulse in terms of spinning? Could something go from not spinning to spinning? Could you apply a force to something and cause it to speed up? If you've got a washing machine or a dryer, you've probably got some spinning that occurs in your home. If you've got a dishwasher, it has that thing in it that spins around and around, squirting water everywhere. Okay, there's lots of circular business happening, and it has to start and stop. And anytime you've got a force applied to a mass, you can have it speed up or slow down, change its momentum. But instead of a force, what would it take to change the angular momentum? Torque. So if we apply a torque to this system right here, we can get a change in angular momentum. And, oh, what would change? Or what could change? Just the angular speed? Oh my goodness. Couldn't you change the moment of inertia and therefore the speed changes? So this is where it gets kind of crazy. We can have a change in the moment of inertia or times omega, or we could have both or one. We have to have at least one, right? Or we can have a change in angular momentum because maybe the moment of inertia stayed the same, but the speed changed, the angular speed changed. Or maybe both things change. We can have a change in angular momentum if we have a change in the moment of inertia and a change in the angular speed. Why not? We can have a change in linear momentum if we change the mass. That's also fine. You have a rail car that's being filled by a funnel system. Remember those related rates questions from calculus? Yeah, you could change the mass of the car and therefore the momentum would be changing too. Isn't that crazy? All right, so in general though, the idea is that we can change the angular momentum by applying saying not a force, but a torque. Very good. So change in angular momentum would occur because there is a torque applied over time. Or we could write it as the angular momentum is the integral of torque dt, which is also like torque is equal to what? The derivative of the angular momentum with respect to time. So everything you can do with linear quantities, you can also translate as, or make an analogy for rotational motion. So a lot of this stuff is the same stuff we've covered before with linear motion, but now we're going to put a spin on it. Ba-dum.